Okay, so today we're going to discuss, I'll finish like just like this network flow example. We were almost done with it, but I'll remind you what it was saying, and then I'll discuss in the last topic for the course, which is like it's called disjunctive optimization, which I thought it is like a nice way to end because it uses like it is on non-convex sets, which is kind of, but you can relate it to convexity, obviously. So it's like a nice thing to see. So kind of my plan, I already posted the PDF of problems, and I posted like a separate PDF, like the one that says solutions. That's the one that has the answer key. But regardless, like, so like the plan for Monday is like kind of like what we had been doing for the other classes were like the other exams were like I would just come here, and if you had any questions, like you could ask me about it. We will have since like the since the exam is on May 12th, there will still be an entire week. So I'll see if I find another time for like if you want to ask me questions besides like next Monday. I'll just try to decide what would be a good time. Um on like next week, but I'll let you know.
Would Monday be the all-star stuff?
I would still be here like answering questions. Yeah, yeah. I'm just saying like as an extra. So, uh, but yeah, I'll just try to think about a good time that would work. Okay, so I'm about to copy. Let me copy paste. Let me first explain the last thing I was telling you Monday, and I'll copy paste it here to finish it off. So last time I was telling you about this flow example, which is kind of like you have a graph, which sometimes is also referred to as a network. The way it's thought about it in this case is what you would call like a directed graph, in the sense that the edges have like an orientation, so it matters where you start, where you end, and also the way this one is thought of is that there's a special edge called the source, sorry, a special node or vertex called the source, and a special node or vertex called the target. So kind of like the idea in this type of problems is you're trying to find a path that takes you from the source to the target. Okay. So again, there are different possibilities, as you can see in this diagram, based on how I drew it. Okay. So what makes this like a problem interesting is that you can think that to each edge, there's a certain cost for taking that particular path. So if you think about it as a road and trucks driving on the road, so that would be kind of like the cost, kind of like paying a toll or a fee for going along that road. And then the other thing that makes this one interesting is that there's like a time. So you imagine that each edge takes a certain amount of time to travel through it. And so what I was telling you last time is that for these problems, what you want to do is kind of like minimize the total cost from moving from source to target. You want to minimize the cost, but under the constraint that you don't want to exceed a certain amount of time. So like for example, you have to travel the network in less than 24 hours or whatever. But this type of problem doesn't have the requirement that you have to visit all the locations. It's just that you just want to go from source to target. Uh, like the ones that you visit all of the locations at least once, it's called like the traveling salesman problem, which is also like a famous problem in linear optimization, but I just decided to mention this one because it's more related to this Lagrangian relaxation that I was telling you about on Monday. So let me just to kind of remind you what the idea was, is that kind of like the logic was to introduce a binary variable for each edge. Okay. So again, like a binary variable are things that are either 0 or 1. So the idea is like the binary variable is turned on, or like it becomes 1 if the edge happens to be part of the route that you take. So it's at 1 whenever the edge is part of the path, and it's 0 otherwise. And so if you do it that way, the total cost that you have to minimize in this particular example, because there were 8 edges, because there were 8 edges, you can rewrite it in this way. And the time constraint that's the one that I had written before, can also be written in this way. Okay. But what I can mention is that there's still some hidden constraints in this problem, because it's kind of like a conservation law that if you think about it in terms of cities, if you enter through a city, like you have to get out of the city eventually, right? So like, for example, in this case, like if you choose this path and you go from the source to this vertex, then once you get to this vertex, you have to get out of it. So you can either get out of it through the top edge, or through this vertical edge that you see here. So the conservation law is kind of like that whatever comes in has to go out in either of these two ways. So that gives you like extra constraints on the variables, which is what I'm about to write. So like sometimes, again, like a lot of like the difficulty in these optimization problems is like, actually, how do you find the correct model? Because once you have like the model, like then you just plug it into the machine and like it will spit out the answer, right? Like no one ever solves this by hand. So it's just like it is easy to miss out constraints or other things that. So you have to be absolutely sure that there's nothing that you're dropping like from the problem. So I'll just kind of copy the the graph in the next one. And I'll kind of mention like, let's call them conservation law constraints, because literally it is some sort of conservation law. So like what I'll do is kind of like, I'll call the other vertices, I'll give the other vertices some names. So source and target, they're already reserved. And then there are other 4 nodes that I have to worry about. So I'll call them V1, V2, V3, V4. And if you see the problems that I put on the PDF, I labeled them for you, because otherwise, like, I would go crazy trying to see which one, what you meant for by each of them. So I would kind of like give you the name for like each of the nodes. Um, so like just like continuation of the last time. So we have like this constraint, like conservation constraints. Like you can think of it as some sort of like mass conservation. And so you get one per vertex, or per node, one for each node. So let's start with the source and target, because they're kind of like special in the diagram. So, but they kind of like are all found in exactly the same way. Like, like, so from the source, kind of like the idea is that something has to, if you're the source, like you have to either take this route or this route. So something has to come out of it. So the way to write that is that 1 should be delta 1 plus delta 4. Okay? Oh, sorry, x1 plus x4, because that's what I was calling the variables. Is that sometimes deltas is also used. Sorry about that. Oh my God. No, this is fixed. Okay, so let's think about what this is saying. So again, why x1 and x4? Because then this edge was h1, this is h1, and this is h4. That's why it's related to x1 and x4. And then why is this equation? Because again, each of these variables is individually 1 or 0, right? So the only way for them to add up to 1, right? If both are either 0 or 1, is that exactly one is 0 and the other is 1, right? Like that's the only way two binary numbers can add up to 1. Only one can be 1 at a time. So what that means is that, and 1, again, like it's kind of like almost like you can think of 1 as true or probability theory, kind of like with certainty. So this is kind of like a way of reading this in probability terms, is that with certainty something came out of the source, but it just had to go either up or down. And so the way we interpret this is just like saying that x1 plus x4 should add up to 1. Is that making sense kind of like so far, so good? And you see like the others kind of have similar interpretations, because they like for example for this one, for the target, the target is kind of like a sink sometimes, like if you think about it in terms of a fluid. So this is called source and this would be called like a sink. So everything has to enter the code into the target eventually, right? So again, with probability 1, everything has to be reabsorbed, but you can only be reabsorbed from either H3 or H6. So 1 should be X3 plus X6, okay? And again, this can be used in electrical engineering. If you think about it, it's an electrical circuit, and then like the resistance of the circuit could be related to the cost, because like, that is where like energy dissipation happens or whatever. Like, you could give these many different interpretations, or like actually traffic flow, supermarket store chains, like, supply chains, whatever. Like there's like tons of um, interesting questions like that you can use here. Um, And if you kind of like, if you Google about this and read some of this stuff, like these problems are called NP hard. And that's kind of like a problem that like, like that, in a sense, like easy, if you have a solution, it's easy to verify in polynomial time that the solution works, but it's not that it's one that's easy to find in polynomial time. I mean, there's like all this complexity theory in computer science for like classifying like how fast an algorithm is, but like these are called NP hard. Okay, and then you kind of like go through the other vertices or edges in the same way. So vertex V1, what is the constraint coming from V1? Well, again, the idea is that whatever, like the way to think about it is that whatever enters must escape, right? So whatever goes in must go out. And so what is going in, what goes in is X1, and then what goes out, then you can go out for vertex 1 either through X2 or X7, right? Edges 2 or 7. So that's one way to like interpret this equation. And again, because this is a binary variable, it's either 1 or 0. So, the idea is that if this is 0, right? Um, this is like the fun part to analyze this. If this is 0, that forces these two to be 0. So that means that nothing went through there. And if this is 1, that forces one of these two to be 1. So that means like, then you choose one of the other paths. So everything really works magically, like it's kind of like fun but it's kind of like fun to kind of like test it out in your head with giving values of 0 or 1 to make sure like everything is actually okay. And then vertex 2, again, it's kind of like the same philosophy. What goes in? Now stuff can go in from either H4 or H7. So in this case would be X4 plus X7. And then how can you escape? You can escape through 8 or 5, right? So it would be X8 plus X5. Is that okay? Is that making sense? Okay, and then there are only two more vertices to analyze. So vertex V3. So for V3, what comes in, you can come from into V3 from H2 or H8. So in this case, 2 plus 8 should, and then you can only escape through H3. So that would be X3. And last but not least, vertex V4. And then this would be what? You can only come in from with H5 and you can only escape with H6, right? That makes sense. And of course, this all depends on the specifics because we're not interested in solving them per se, but like in a really like in this particular problem, just because of like how the equations happen to work, that means like for example, I mean, like you can kind of reduce a variable sometimes, like because that means that every time you see x5, you could replace it with x6 if you wanted. So that allows you to drop the number of variables by one. And in others, you could solve like, like kind of like a lot of these equations you could use to solve for one of the others to kind of like reduce the number of variables. Of course, like there are more like efficient ways to solve this. I'm just trying to say, like, if you try to solve it by brute force, that's some of the things you could do. But we're more interested in just setting it up, understanding that, like it is related to Lagrangian. And so how is it related to Lagrangian? Maybe I should like that's what I'm going to tell you now. But are there any questions about how I found the constraints? Like, is that making sense? So just remember that we had this extra constraint from before, like the time constraint from last time, like which we wrote last time, which was that the sum of the times should be less or equal to the a total amount of time that you were allowed to travel through the circuit, right? And the philosophy of this Lagrangian relaxation is that you choose, again, the point of Lagrangian relaxation is that you call certain inequalities hard and others easy, So kind of like all of these are like of the same nature because they are all related to the vertices, right? Um, so all of these are kind of like the same type of inequality emanating from the vertices. And this one is kind of like related to the time constraint. And in principle, this is like the only one, if you look at it as the expression, is like the only one that for sure would involve all the variables, right? Whereas this one's kind of like depends on like the actual specifics of the graph, whether like, there are 5 variables involved or 3 variables involved. So if you just had to make a guess, again, like even if you have zero experience doing this, you could think, well, maybe it makes sense to kind of like think of this as a hard one just because like everything is involved, right? And it's like actual inequality instead of like equalities. So kind of like like one way to try to solve these problems as like an approximation is to interpret this as the hard constraint, okay? And what's the point of the doing the hard constraint? That you forget about it and you just reabsorb it into the function. So the function that you would work with, like the modified function, which I think I called like last time the Lagrangian function, So you like, and again, I'll just kind of finish writing this, but you would like, I'm just telling you, if someone were actually interested to know how this is solved, you would work with the modified function. Well, you would try to find the mean of this function of like the sum of the cusps plus lambda sum of ti's xi's minus t. So that is what the function will look like, which in this case lambda again is non-negative. Remember the reason why, if you remember how I wrote this last time, the thing is like now because this one is a mean, it makes more sense to kind of like put the variables first. Because just for if you remember, when you have like an inequality like this, and the way it would reappear in the Lagrangian function, it was like plus lambda b minus ax. So like the constant term was appearing here first, and here like the variable term appears first. But that's because like in the way I wrote things last time was with the max, and this is with the mean. So if you remember a max, a mean is minus a max, so that's why there's a minus sign overall difference. So again, like I just wanted you to see how, like, it would look like, which has like this like economics interpretation, because one way to rewrite this is as a mean of, if you factor out xi's, this would give you ci plus lambda ti minus lambda t right? So in economic, like, if you wanted to do like a economics interpretation for this, like kind of like the idea is that you're kind of like based on the time it takes you to go through the particular path, you kind of like add like a cost to it. So it's kind of like, like this was the original cost of the path, but the lambda TI is kind of like an extra surcharge for going through that path. So it's kind of like you are monetizing the time that it takes you to go through a path. So like if it takes you 4 hours to go to a path, maybe the penalty for it is that now this path costs them more dollars. That's kind of like how you would think about it. So it's kind of like a conversion of time into cost, right? Like that's what like this lambda does for you. Like it's kind of converting time into a cost penalty for the time. So it's penalizing the amount of time. So penalizes you for spending a lot of time on a particular road or spending time on a particular path on an edge. So you see, like because lambda is positive, the more time you spend on it, right? The higher t is, the more this contributes to the sum, right? So the cost kind of like increases, like which so it's all very kind of like intuitive and plausible. Uh, so all of these things like have like nice like interpretations in terms of like a penalty. That's how it's thought about in economics terms, with prices and other things. Is that making sense?
What's the penalty versus that? Like economically.
Oh, that actually, I mean, I guess here, I don't think like because it's just like a bound. I don't know. Like it's unrelated to the verb, so I don't know what would the interpretation be in that case. Because if for a fixed lambda, right, that this minimum, right, to minimize this, you only have to minimize this quantity, right? Because for lambda fixed, this is a kind of like a constant. So I don't know if they kind of try to give like a specific meaning to the big T. Maybe they do, maybe they don't. But I would like I think that's kind of more ambiguous to me because it doesn't play a role in the actual minimization. The only thing I think it kind of like works as is a kind of like an upper bound, like because like for example, how would you drop? Here's like one way to drop the bound is to let t go to infinity, right? If you take t goes to infinity, like this kind of like constraint kind of like is irrelevant, right? But yeah, it seems it doesn't kind of relate in a specific way to any of the variables. I don't know if they give it like an actual meaning, but maybe there is. I'm not sure about that. But yeah, like I did like this method because I thought, okay, I like this Lagrange and stuff, so it's like a good one to have, to know that it exists. Like again, like a lot of the point of this class is just for you to, if you ever need to use these things, like realize, okay, there was this time long time ago where like this was like Lagrange relaxation was mentioned, and then you go, okay, you go back and find it. Okay, that's kind of like my philosophy with all like these classes, especially for something like this where it has so many applications, which is like overwhelming sometimes, like how many applications there are for linear optimization. Okay, and then the other one that's kind of cute, which I wanted to tell you about to finish the course, is like this disjunctive programming. So okay, last topic. So it's called disjunctive. So, okay, I'll kind of explain first, like just the word disjunctive. So, not sure if, like, if you have taken ever like a course that does like logic or discrete math, but in logic, there's a thing called like a proposition, which can be true or false. And so, for example, like, in logic, you have things called propositions, which are true or false, right? So there are statements like sentences that can be true or false. So a proposition, usually the propositions are written uppercase P. So a proposition, like a first proposition could be like, I like pizza, like something dumb, like, So that's either true or false, right? Let's say. And second proposition could be like, I like ice cream. And so if I say I like, there's another proposition you can make out of these, which is, for example, I like pizza and I like ice cream. And that and is called a conjunction. So P1 and P2, which is just I like pizza and I like ice cream, is called like a conjunction of these two propositions. So okay. So like the word and is in logic is related to the word conjunction. And like there are other ways to write this, like another way to write this, which you may have seen if you ever take kind of like discrete math or something like that, is kind of like this weird symbol for the and. That's just kind of to simplify things a little bit. They mean the same. I'm not going to use it, but I'm just letting you know that that's how they would look like. Now, conjunctions or ands have been secretly important in this class because all the inequalities that we were working were implicitly ands. So, for example, when I would write like, we have been working all this time with ands. Like that's actually what we were doing. Like, so for example, if I wrote like the max of, I kind of was lazy and I would write 2x plus y, right? Where like x is greater or equal to 0, y equals greater to 0, and then I would write something like x plus y less than 2, and then like, I don't know, like let's say x plus 2y less or equal to 3, right? Like secretly that was saying x is greater or equal to 0 and y is greater or equal to 0, and like there are ands all over the place here. So this, if you wanted to write it in like this proposition language, you know it was x greater or equal to 0 and y greater or equal to 0, and x plus y less or equal to 2, and x plus 2y less or equal to 3. And so there's like a proposition, like you can then rewrite all of this in propositional language, because like the first proposition is just saying that the proposition 1 was that x is positive, proposition 2 was that y is positive, proposition 3 was that x plus y was less or equal to 2, and proposition 4 was that x plus 2y was less or equal to 3. And the reason why ands are so important, or conjunctions, is because the intersection of convex sets was convex. So that's why all the theory worked well, because like we kind of like did that very briefly, but the and is related to intersection in sets. And so inter and like corresponds to intersections, and intersections of convex is convex, and that's why all is great. And corresponds to intersection. And the intersection, let me write this word properly. And so that's why like all of this theory is kind of like nice, in a sense. But then there's this other operation in logic which is very important, which is called like the or, right? So like you could have like proposition P1 or P2, which in my original example would have said like that I like pizza or I like ice cream, right? And that is called like a disjunction of proposition. So that's where like the word disjunction comes from. And that the OR in logic is related to the union operation in set theory. So like an OR is, if you remember of like these Venn diagrams, it's kind of like a union. Okay. So this is related to unions in set theory. Related to unions in sets. And so the problem with ORs from our perspective is that the union of convex sets is not necessarily convex. And we had mentioned that very briefly, but I'll kind of like draw a picture like right away. So why are unions not that great for us? So unions are not great, are not so good in our case. Because union of convex sets is not convex. Unions of convex sets is not convex. So here, like you can get creative. So like let me show you like one example.
They're not always convex.
Right. Like yes, like true. I'll just say it's not always convex, just to be completely correct. Yeah. Good catch. Yeah. Always convex. So for like here's like a here's a very basic example. Imagine taking two triangles. I'll work with these triangles in a moment, so I'll kind of like may try to write them like in somewhat detail, but let's see. If you take this triangle, like it doesn't matter which one I draw, but like imagine taking this triangle. This is a convex set, right? And then let's take this other triangle. Oops. Which is also convex, right? I'll give specific inequalities in a moment. So like you can think that the first convex set is the first pink triangle, the second convex set is the green triangle. The union literally corresponds to the stuff that has been painted at least once, right? Like it's like, and this is clearly not convex. Like you can take a point here and a point here, and that's it, right? Because convex meant that every segment is entirely contained in the in the region, and this you can easily see that this breaks that condition. So not convex, like union not convex, right? And there are like other like funny like like you can draw like kind of like the plus sign. If you draw a plus sign, right? That is clearly not convex, but you can think about it as a union of two rectangles, right? Like actually, let me try to make it a little bit better. The plus sign, like the operation plus, like you could think about it if you wanted as a union of two rectangles, like here, and each rectangle is convex, right? And so there are tons of like fun shapes in the world that are not convex and like nothing wrong with them. Like the plus sign is not convex, like for example, but it's a union of convex sets. So it would be nice to have like a way to, of course, like here's like a, if I said, oh, try to maximize a function over this region. One option would be, okay, let me just find the max over the pink triangle, find the max over the green triangle, right? Kind of like pretend that they're separate entities, and then just take the max of the, find the individual maxes and just take the max of the two. Like, and that in a sense is fine, but it's kind of like useful to realize it's as a theoretical thing that and there's this area called disjunctive programming. So it's something that people actually use. That there's like a way to rewrite this using binary variables. Yes.
If you want two convex sets to be like unit of two convex sets to be a convex, one of them must be a subset of them, right?
That's what I was thinking now. Like could sound let's see. I want to double. I mean, not necessarily because you could have I mean that definitely would work, but like here's like one that if you kind of like stack the triangle, I mean like you might think this is cheating, right? But like that's how math works.
Or maybe overlap.
right? Like, I mean, but you know, for example, you could take half a triangle, half a triangle, and then the union is like a square. So you like kind of trying to find the correct condition for when the union is convex. At the top of my head, I don't remember if there's like an easy characterization that is, you know, like doesn't seem like, because you could kind of like do something like this, where like the faces, if it agrees on one of the faces, like at least in the two-dimensional case, it would seem fine. But like you have to be more careful than just saying that one is containing the other. You see, yeah. No, but like but let's say that in general you wouldn't count on it to happen, right? And that's good enough for us, you know. Because this is like a very like a little bit of a cheat. You know what I mean? Like because it's like very well carefully crafted so that it would work, the union. So but okay, so what I was saying is that it's kind of like interesting to know that in like, you know, that you can kind of like represent okay, so I'll tell you philosophically what's happening. You can represent this union as a convex set but in higher dimensions. So and then this becomes the shadow of the convex set. So that's kind of like interesting to understand it kind of from a philosophical perspective, that in higher dimensions, you can find a convex region whose projections, that's a technical word for it, gives you back I'll write the trick. And I thought, oh, this is so cute. I'll mention it in class because I like this a lot. So this is kind of like the trick of high dimensions. Sometimes by going to higher dimensions, you can, it's kind of like the slack variables. Kind of like the point of slack variables is to turn inequalities into equalities, because in a sense, it's easier to work with equalities, you know, but the price to pay is extra dimensions. So it's kind of like a similar philosophy here, that by going to extra dimensions, you can kind of like find a convex region that characterizes like that union, which, like, you know, well, in a way that I'll make more precise in a moment, okay? But that will require this trick of binary variables. So, but okay, just to make my life easier, I'll assume I'll tell you how to do this. So I'll explain how to use, and the union could be of any finite number of sets. So you could have like a union of 100 convex sets, and once you see how I do it, you'll see that it can be generalized. I'll do it for 2, but once I give you like the formula, you'll see, oh, okay, yeah, of course, like you can do it for like in general. So I'll tell you how to write a max problem on a convex set, on a union of convex sets. And then I'll show you an animation because that's very cute. In terms of a higher dimensional convex set, let's just put it like that. In terms of a higher okay, my let's see. So how should I want to explain this? Okay, my only assumption, like, and it's something that can be relaxed, but I just want to make my life easier because I just want to illustrate the point. The only assumption that I will use is that the convex sets are finite. Okay, so I'll just assume that what's called bounded. So I'll just assume that each convex set is bounded. I'll assume.
Always has to be finite, or like just for simplification.
No, just for simplification, there's something called the recession direction. If you want, I can send you like more details about it. But yeah, like there's something called the recession vectors, and they have to be the same for all the convex sets. It's just that when they are finite, there are no recession directions, so there's nothing to check because there's nothing that has to agree. So it's just like a little bit easier to do it that way. Okay, but if that happens, so what I mean, like, if you have like a bounded set, yeah, like, you know, just imagine like having like a convex region, like again, like a convex region is kind of like and like the types of problems that we're working with are kind of polyhedra. So like it could look like this, for example, like maybe this is kind of like the polyhedron that represents one of the convex sets. So anything that's finite. So my claim, I'll kind of write it as a lemma because that's what will make everything work. Once we have that, it will be easy to see what the solution is. But my claim is that if the convex set So I'll think of a convex set as being given by like we have always been working with non-negative variables, and the convex sets that we worked with on this class always had like, we were writing them as ax less or equal to b. Let's see, I should then there's no let's by finite I mean bounded. Then there's no vector which satisfies and then a x r less or equal to 0. Let me write this a little bit better. It satisfies. This vector is called like a recession vector if it were to exist, and that does go back to your question about whether this can be relaxed. So these vectors, if this existed, if this vector existed, it would be called a recession vector. If this vector existed, okay, I'll show you. It's actually like I'm writing it in a weird way, but it's like a very geometrically intuitive idea of what I'll show you what it means in terms of a picture if you have that vector. Essentially, what it means if you have a vector with this property is that you have like a ray, an infinite ray inside the region, like so, and you'll see why that happens in a moment. So, uh, so why is this vector impossible? So let's answer that. Why is this vector impossible? Because let's say that you had a region, a convex region. Um, okay, let's say you have a point on the convex set, right? And then you have this vector xr. Maybe this vector looks like this. I don't know. The vector doesn't have to be in the convex region or anything like that. But what I'll do is kind of like use that as kind of like a direction. So I'll kind of like consider, I'll consider this vector. So I'll rescale it. This is t times xr, right? And if you remember vector addition, how it works, you just add them by using the parallelogram law. So it's like this sum would be this one. Is that okay so far, so good how the picture looks like? My claim is that this picture is accurate in the sense that this new vector is inside the convex region again. So what I want to assert is that this vector, the sum vector, the added vector belongs to the convex region. So I'm going to say, so my claim is that for any t greater or equal to 0, for any rescaling t, the vector x plus txr is in the convex set. Okay. But what do you need to check to do that? You need to check that it satisfies the inequality to be in the convex set. So you have to multiply this by the matrix A and check whether or not that's less or equal to the vector B. So what is A times x plus txr? Well, if you remember how matrix multiplication works, that's ax plus t times axr, right? Ax is less or equal to b because like the vector x is in the convex set. So this one is less or equal to b. And then this is less or equal to the 0 vector. There you go. Like this is just like b, right? So that's saying that if you have this magical vector, you can just kind of like move in that direction and you kind of have like an entire ray inside the convex set, which cannot happen if the region is finite, because a region that's finite cannot have any infinite, semi-infinite rays inside of it, So it violates the finiteness. So there you go. Like, so it's kind of like easy. So it's kind of like, which is actually like an interesting lemma in its own right, like to know that that cannot happen, like, with finite regions. So it's kind of like good. You'll see where that shows up in a moment, where I give you how this works in general. Okay, so let's say.
It's geometrically intuitive, but like, what rule is conflict in geometry?
So what, like you're saying that geometrically, what would
Yeah, geometrically it's intuitive. Like I see.
right,
Like,
yeah.
In algebra, what rule is conflict?
Well, it's just that, like if you had like, if you had like an entire array, like algebraically, if you had like an entire array, a array is always can be written this way, where like b is like the direction of the vector of the array. And so if this is actually, I had like this problem long time ago as a problem in class, like for the first exam, I think, but like I would have to go through it. If you divide if you divide every side of the inequality by t, then you get ax over t plus av less or equal to v over t. And then you take t goes to infinity. And then you get av less or equal to 0. So you can see kind of like algebraically that if there's like an entire array, if there's an entire array, a times v has to be less or equal to 0. Yeah. But it's just something that will pop out in a moment when I guide you how to find the convex set. And so it's kind of useful to know that this is ruled out. Okay. Okay, so let me just show you how to do the union thing. So let's say you had let's do the union. I'll write it like on the plane just to, and use like I'll do it kind of like a little bit more abstract than what I intended, so that you can see that there's nothing really too specific that I'm using. Okay. So let's do the union of two convex sets. So I'll call the convex one convex set A and the other convex set B. Okay. I'm drawing it on the plane, but you'll see that I'm not using anything on the plane that's related to it. So like, but let's say that the first convex set is like, let me draw like, I'll try to draw them as polyhedra because, let's see. So this is a convex set A. I don't want to, or should I call them? Let me see. This is where like this becomes, okay, I'll call it C1 for convex set 1. Okay, sorry about that. And then like you could have another convex set. I'll try to draw like kind of like a triangle of sorts. Or maybe it looks like this. Again, they don't need to intersect. They could intersect everything, like, like that's totally like, like arbitrary. They could be disjoint, which would be the word for saying that they do not intersect. The only thing that I'm going to ask about them is that they are bounded. So like convex set C2. Okay. And so like imagine I gave you like this problem that you're trying to find the max of C dot X, right? Like usual stuff where X is greater or equal to 0. And the first convex set could be represented in terms of a matrix, right? So let's call it A C1X less or equal to B C1. That's the C1s is just to say that that's a matrix related to the first convex set, right? Given by the first inequalities. Or, and that's where the or comes in. Like so this is like the new thing that we had not used before. Or um, a C2 X less or equal to B C2. So again, this is like the matrix related to the second convex set, the vector related to the second convex set. And again, emphasis on the or here because we didn't have it before. So like like for example, if like we can do like something easy, like if you like the things like this convex sets, like for like if like this convex set, like as an example to kind of like before continuing, like if the first convex set had been like 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 yes like let's see. If the first convex set had been like something like this. Let's say the matrix, like it had been two triangles, which actually is what I wanted to do at the beginning. Then like I could have asked you to find the max of C1 X1 plus C2 X2, where like x1 is greater or equal to 0, x2 is greater or equal to 0. So the first inequality for the first triangle, you could write it as 3x1 plus 2x2 less or equal to 6. Okay. Or the blue conditions would be that x1 and then minus x1 plus 4x2 like 0. So what I'm saying is that you're looking at a max, right? Where, let's see if this makes more sense, where the variables have to be non-negative, right? And then either 3x1 plus 2x2 is less or equal to 6, or this happens, right? By the way, this or does allow for both to happen at the same time. So it's not like a disjunctive or. But all that I'm saying is that you could rewrite this in matrix notation, and that's what I'm calling AC1. And you could rewrite this in matrix notation, which would be the matrix AC2. Is that making sense? Is that better now? Okay. So the solution, which is like a very clever solution, like actually. The solution is to you introduce binary variables. As always, binary variables are your friends because you have a binary variable to say 1 or 0 that either you're in the first convex set or the second convex set. So there will be a binary variable for those. I'll call them delta 1 and delta 2. And then you double the number of variables in the problem. So kind of like you kind of think that the first convex set has its own variables, and then the second convex set has its own separate variables. So like the solution. So the way to solve this problem. You introduce binary variables. Okay, again, I'm only doing it for two convex sets, but you'll see if you had wanted to, like how you would do it for like for more. So delta 1, the meaning is that delta 1 is exactly 1 whenever the point happens to be on the first convex set, and same word for the other one. So delta 1 is 1 if the point is on the first convex set. And 0 otherwise, right? And delta 2, I don't want to call them x1 and x2 because those names are kind of like reserved. And then if the point is on the second convex set. Okay. So that's the first step. You have binary variables, and then you double all the variables in your problem. So originally we had 2 variables, right? X1, X2. I will double that, and that becomes like 4 variables instead of 2. So like this is step 1. Step 2 is to double the number of variables. So and they're completely, think of them as new variables if you like. So these are new variables, which I'll call called x1 c1, x2 c2, x1 c1, x1 c2, and x2 c2. So hopefully the meaning is kind of like making some sense. Like kind of like I want to think of this as kind of like a version of x1 and x2 for the first convex set, and I want to think of this as a version of x1 and x2 for the second convex set, if that makes sense. Um, so and they're completely, think of them as new variables if you like. So these are new variables, which I'll call called x1 c1, x2 c2, x1 c2, and x2 c2. So hopefully the meaning is kind of like making some sense. Like kind of like I want to think of this as kind of like a version of x1 and x2 for the first convex set, and I want to think of this as a version of x1 and x2 for the second convex set, if that makes sense.
Also.
Hmm?
They can be in the first one, for first convex set and the second convex set at the same time, because there is a.
Oh, right. So the way the binary variables will take care of the fact that you won't count twice the same point if it happens to belong to the intersection. So yeah. So no, like that is taking care of it. You know. So let me show you. Oh, sorry. Yes.
Where's C coming from? I thought,
Oh, C. That's the letter C. You mean?
yeah,
Oh, that just sorry, just to go back, the C's were the names that I'm using to refer to the convex sets. I could have used A or B actually. Like, I think that could have, like, I could call this convex set A and convex set B, and then this would have been like X1A, X2A, X1B, X2B. Like maybe that would have been better actually. But I guess Z for convex, and then so let me just kind of like show you how this will look like. And it's very, I mean, it is, what I like about this is that I do find it like a very clever solution. Like, and because it kind of like turns the problem into higher dimensions as a single convex set, which I do like, I did find very elegant. So I thought, oh, I'll finish by telling you this. Did I write this? Okay. So I'll write it this way. So the way I will turn the original problem into the following problem, which is like the new problem. And you'll see why it's kind of like equivalent to the previous one. It's kind of like fun to see. So it will be the max. Right, like remember C, like, oh, C, C1, C2, right? So I'll write it more like in dot product notation so that you see what's going to happen. C1, C2 dot X1, C1, X2. Oh my God, sorry, this should have been C1, sorry. Right, it's like a copy for each convex set. So X2, C2 plus, no. X1, C2 plus X2, C2. Yeah. And then I do have to multiply them by deltas. Okay, let's see. Let's like I'll do it. Sorry, I'll do it even. It's almost that, but give me a second just to fix this. I'll write it in a slightly more convenient way representation. Okay. Let me move this a little bit. Yeah, I forgot about this part. X1, C2, X2, C2. So like kind of like, like I'm thinking about, I'm kind of like splitting, like really there are like 4 variables, right? So it's like a vector of 4 entries. I'm just like, for convenience, I'm splitting it into 2 entries each because, and weighting each by delta 1 and delta 2 by the binary variables, right? Okay, so far so good, like at least in terms of the optimization function, right? Because what, like again, each of these variables is either 1 or 0, right? So if let's say the first one happens to be 1, that forces the other one to be 0, so you don't see, and then this one becomes a 1. So this is exactly the same expression as before for the optimization function, right? And same goes if this one had been 0 and the other one 1. And it doesn't allow you to both be simultaneously 1, which means a point is not overcounted, right? If it happened to be in the intersection, right? Like, because then it would double the like double the value of the function. So it's kind of like good in the sense that it also doesn't, uh, overcount a point if it happens to belong to the intersection. So far, so good, everyone with me? Okay, and then I could have put this at somewhere which the usual thing where each of the variables is non-negative, which is not a surprise, right? We have done this every single time, but I'll just put it for completeness sake. Kind of like the clever way, the clever thing is like, what do you do with the inequalities? Like that's actually where the meat of the problem is. How do you deal with the inequalities? So the really cool way to do this is that you take the first inequality, right? By the way, this is what I'm calling X C1, which makes sense, hopefully. And then I'm calling this X C2. And I'll kind of mention that, let me introduce that this is like the difference from before. So the only thing that I'm going to do is multiply the constant term by the binary variable. And you'll see that that kind of like makes the magic happen. It's like a very clever thing. But the point is that now it's an and, right? Otherwise, like, why would we do in this? So maybe let's go over why this actually gives you what you would like it to give you. So everything is written in very symmetric way, right? Like, so if it works by making one of the variables 1, it will work by making one of the other binary variables 1. So for example, what happens, like if delta, just to kind of like as a sanity check, right? What happens if delta 2 happens to be 0, right? Let me just show you. So if delta 2 happens to be 0, this goes away, right? And that forces delta 1 to be 1, right? Now delta 1 is 1, so you don't need to worry about that, right? This inequality just becomes like the regular inequality, right? Which is like kind of what we had from the beginning. And this one becomes the 0 vector, right? Right? But now this is related to this lemma that I wrote before, right? Because the sets are bounded, there are no recession vectors, or I should have said no non-zero vectors, right? Like this actually forces this vector xc2 to be 0. So like which is fine, like so like the problem, this forces xc2 to be the 0 vector because like the convex set was finite, since convex set was finite. So that inequality kind of like disappears for free. So you end up with the inequality for the first convex set. So it's like a projection. That's what I was saying earlier, because literally it reduces to just maximizing the function on convex set 1. Like, like the other one, it's not like an extra condition you have to worry about. It becomes 0 less or equal to 0, which is fine. So convex set 2 was fine. Is that making sense? Isn't that clever? It is very clever. So in my opinion, and kind of like the same goes with the other one. Like if you had set the other weight equal to 1, right? Then you see like the stuff with the second convex set. Now this one is the one that's 0, which again just gives you the zero vector, and then you get like the one that unmodified for the second convex set. So this is like a very elegant way to rewrite, you know, to rewrite the problem in terms of a higher dimensional problem. Like it is insane that you can turn an, like if you think about it from a logic perspective, you're turning an or into an and. Like that is like philosophically what's happening, and that's what you really have to like take a deep breath to appreciate. Like, because again, I put ands here now. There's no more ors, so that's kind of like the interesting to understand. But the price to pay is that you have to use more variables and you have to introduce binary variables. In fact, is that making sense? Kind of. So there's like a the problem is that this is almost impossible to always visualize because like already with something in 2 dimensions, you have to use 4 variables plus 2 binary variables. But like, and this is very stupid as a problem, but you can kind of like do it in 1 dimension, like, and then you can visualize things. So I did kind of like was going to show you that quickly because I did the animations and I thought they were cute. So in in 1D, this can be visualized. And you can work out the details. I'll just show you the animations because I don't have enough time. But imagine that the first convex set had been the interval 0, 2. So this is like the convex set 1. And let's say that the second convex set had been 3, 4. Okay, so those are 2 convex sets, like which are kind of silly. But then, so like this only requires 1 variable, but you have to double it because of what we were saying, right? So you would need two variables, right? 2 copies of x. And 2 binary variables, right? And 2 binary variables. But the thing is like the binary variables, since they add up to 1, I can always replace one in terms of the other. So really there are only 3 variables in this problem. So I can make the problem 3-dimensional. Like if I wanted to graph it, because delta 2 is 1 minus delta 1. So what I can do is kind of relax it and make it a continuous variable between 0 and 1. And let me show you what you see because it's kind of like super cool. I had fun doing this animation. Wait. Okay, so this is A is kind of representing here the value for delta 1. Okay, and so you see when it goes at 0, it gives you one of the intervals. Then it would be delta 2, I guess. When it goes to 0, it gives you one of the intervals, and then when it goes to 1, it gives you the other interval. So it interpolates between the 2 intervals, right? But of course, the picture is 3-dimensional, right? I'm just doing kind of like as a movie. So you have to imagine putting all of these sets together in 3 dimensions where the height is the variable t, kind of like time, and you get something really cool, which I'll show you because it's like again, it's very fun to work it out. And then you get kind of like this pyramid. So wait. So okay, I don't know if you saw that, but kind of like close to, let's see if I can zoom in here. You see kind of like an interval here. Do you see this interval emanating here? So that's like at time 1, like you had like literally just that interval, and it starts as time goes by, it starts growing until like it gives you this rectangle, but then one of the intervals is contained here as well. So yeah, like the interval 0, 2 is like somewhere in here. So kind of like it interpolates between the 2 intervals in 3 dimensions, which is kind of like crazy. And it's a polyhedron, right? Like that's what I wanted you to see. So it's convex. So kind of like the shadows, depending on how you set it up, the shadows gives you like the 2 intervals, which seems like a little bit of an overkill, right? Like just for 2 intervals, you had to make a 3D picture, which seems like a bit too much, but it's kind of like philosophically, again, it's like an interesting idea that by going into higher dimensions, you can kind of like turn an or into an and. Like, when you think about it, like, again, like it's like very impressive. Like, so if you look at the problems for the practice that I put on the PDF, it's just kind of like I give you 2 convex sets and you just write down like the optimization problem with like, the delta 1, delta 2. It's just writing it down as before, but I did want you to kind of like see this technique because I thought, okay, that's actually worth knowing that it's out there because we have only been working with ants. So it's just nice to know that ORs can be tackled, even if it's a little bit like complicated. Okay, so let's end up here. And again, I'll be here on Monday if you have any questions. And then I'll try to find another time, maybe later next week, where if you want to show up to ask me more questions, you can. But we still have time for our exam because it's until the 12th, and I'll send you the graded exams by Friday. I think that should be fine. No, they will be in person. Yeah. And well, Mondays, like, yeah. I do have to come to, because I have final exams and other things for my other classes. I will have to be coming to the department. It's just like, I could do it. The thing is, like, I don't want to wait until, no, it will be in person. Yeah, don't, it's impossible. It would be so annoying to try to do this online because like writing everything. No, so I'll just find a good time to do it.